Hi guys, so Derek here. I will be talking about understanding multimodal LLMs. Hopefully this will be like a series of like interesting summaries of blog posts or papers that I deem as interesting. So this guy is amazing, Sebastian. Highly recommend. I bought his book and I hope to read it soon. So basically, he talks about like how input is given into like multimodal LLMs. So what does multimodality mean here? Multimodality means like you have multiple types of inputs such as text, sound, images, and videos or more. So like the basic idea that this guy talks about is like there are two ways of feeding in like input. Method A and then method B. Method A is like you have like embeddings and then you concatenate them in the beginning here and then you feed it into the LLM. And here in method B, you feed in the text token embeddings and then you feed in the image patch embeddings here and then you feed in the text token embeddings in the beginning and then you feed in the image patch embeddings in the masked multi-head attention layer. So this is a transformer architecture, and then we will talk about an example, the specifics later. So this guy talks about here. Yeah, so here you have like a tokenizer and then you have an embedding layer. Usually like the tokenizer is usually uses byte pair encoding. I think that's like pretty state of the art right now. And then you get this text and then you have the embedding layer and then you basically generate the text embeddings. Text embeddings are like I think vectors of like x dimensions and yeah. But they're usually like concatenated together and then they're passed to the LLMs. So yeah, understanding image encoders, if you're given an image, you basically want to generate the image patch embedding. So how would you do this? So patch means like you split it up into like X parts. This guy particularly specifically split into 9 parts, and then he does the linear projection, and then he generates the embeddings, and then the transformer encoder. The image encoder, such as like clipped or VIT, it's used to be called, and then here, yeah, they generate the embeddings there, and then this is fed to the MLP head for classification. Yeah, so here you have an image patch flattened into a 256 dimensional vector is up projected into 768 dimensional vector. So you have 16 by 16, that's 256, and then this is 768. So what we have is like you have 256 and then you multiply it by a 256 by 768 matrix, and then we have this, and then this generates x is equal to 768. Does that make sense? Yeah, so let's say like this is of dimension 1, so 1 by 256, this is like the dimensions, and then if we multiply that, sorry, I will use a pen here instead of making sure it's vanishing. So 1 by 256, that's a vector, right? And then you generate a matrix of size 256 and 768, and this generates a new vector called 1 comma 768, and that's like called like up projecting. And you can multiply these together because they're of the same dimensions. So he basically talks a little bit about the PyTorch core that does this. So he talks about like a patch projection layer. It has multiple steps, the initialization, which has 2 parts, and then you have the forward multiplication. So here, if you look, you have the patch size, num channels, embedding dimensions, and then the projection is defined as such. And if you see here, the patch size is 16, and then the number of patches is 9. So once the example usage, they're defined here, and then the projection layer is defined as such. So you feed in patch size, number of channels, and embedding dimensions, 16, 3, and 768, right? So this is initialization part 1. and then he does a different initialization, like patches, and then he generates a random torch tensor with 1, 9, 3, 16, 16 as like the dimension. So this is a second initialization. So why does he do this? So if you look at the PyTorch code, you have self-dot projection. So you have 16 by 16 by times 3, and this this becomes a 768 by 768 matrix in our specific example. So it becomes an n by n matrix. So if we multiply that with the projection as a projection layer, what we do is, so if you do projection layers, if you call the projection layer as a function, it basically implements the forward method. So these, we initialize them at first, and then we basically spit them out again within the forward function, and then we reshape this. We flatten each batch. So -1 would be whatever is left over. So the batch size, number of patches align. So -1 would be channels times height times width. So it would be 3 times 16 by 16 in our example. So we reshape this tensor into 19768 dimension. And then here we do x is equal to self-dot projection, comma, like a method x. So what we do is like we multiply this with this projection matrix that we initialized here, and then this will be like back propagated to like minimize the loss and such. So if we do, this is initially what we have. We change the dimension to this. We multiply the projection layer, and then this is what we get. So if you see here, this is what it outputs, 19768. So that's like what the dimensions are. So this specific part, I think, is the projection layer. So it talks about what this is, what's happening here, I think. So essentially what we do is the same, I think. We have initialization, and then we up project it, right? Yeah, so we have an image, we split it into parts here in the image encoder into 9, and then we up project it. So it initially starts as 256, but it will be ended up as 768. So if you see here, we have initially, this is what we have as the initialization, but then we up project it to have 768. So same here, right? So we start out with like 3, 16, 16, I think, and then here we have 768, and then this vectors are fed into, this is another projector, so you project twice. So you project once here in the image encoder, and then this is another projection. So projection like 768 increases to, I don't know, like 1024, something like this. So you increase the dimensions here, right? So rescale to match the text embedding dimensions. So like if text embedding is of size 120, let's say this number 120 is 1024, then we need to also project it again so that these dimensions match. Yeah. So method A is like you have, you concatenate them together and then feed it into the input. So when we see here, you see the image patch, and then you see the text, and then you concatenate them together, and then you feed them into the transformer layer, transformer architecture. And then in this part, you have the option of like introducing like the text embeddings, image patch embeddings in the mask multi-head attention layer, and then this guy goes into like details on how that happens. So let's say this is method A, where we have this basically means like the number of tokens and then the embedding size, but what's going on here is like you concatenated them. So like let's say the number of tokens is like 768, and then we have like 16 and then 16 of them. So this would be, sorry, the embedding size would be 768, and then the number of tokens would be 16 plus 716, let's say. And then here, a simple rule in like linear algebra is like if you have like a matrix of size A, B, and then B, C. This will result, if you do matrix multiplication, if of these, if you multiply matrices of these dimensions, you get A times C, right? So if generally you have a matrices that are initialized randomly, right? So if you see here, they're initialized randomly, and then the weights matrices are generated. This weights is generated, this weights is generated. And then if we multiply these two together, because D and the size D are the same, you have N times DQ matrix right here, right? So you have same here, like this size and this size are the same, so they cancel out, and then they generate a matrix K, and same with V. And then this here, we transpose it, so this becomes like K, and then this is N times DQ, right? And then if we multiply these two together, we generated a matrix N by N, right? And then you do a softmax, and then you get this value. And then we multiply these two together, right? So A, V would equal Z, right? So I think you multiply in that order. So that's why you have Z is of dimension N and DV, right? And here, the Carth engine, this is where it gets kind of interesting. So you have the the number of tokens here. Yeah, so I think this is what initially is passed in, but then this part is where like the image patches come in. So if you see here, right, in this example, in method B, you have the text embeddings, and then they go through a dropout, and then they go to the layer norm layer, and then they enter the mask multi-head attention. And then this is where you generate the image patch embeddings and make sure they're of the same size dimensions, and then you enter and you do the multiplication here. So this is what's going on here in the layer. So yeah, so this is for like text, and this is for images, and then you generate a matrix, 3 random matrices that will be like fine-tuned. No, they will be back propagated later to adjust the weights and stuff. And then you see the D's cancel out, and then you have DQ left, right? DQ and N here, right? So you have Q, and then K, and then V. And then you multiply these two to get this tension matrix, and then you do softmax, and then you do these two, you multiply AV again in this specific order, so the M dimension cancels out, so you get Z. I think you can also have multiply it with this. So or essentially, if this is like images and this is like text, it's essentially like switching the arrow to that goes this way. So if this matrix were multiplied to be this, then this K matrix would depend on this input, not on this input. But if you just switch the orders, then it will essentially be the same thing. So it doesn't really matter. So yeah, just to reiterate, so if you have an image and then you divide it into patches, go through the image encoder, project it up, so increase like the dimensions. You have the option of like feeding it into the original input, or like you introduce it in the mask multi-head attention layer. So that's what's going on. Yeah, so that's I basically had time only to talk about like read the Llama 3 herd of models paper. So these models come in like 11 billion, 90 billion parameter version, are image text models that use previously described cross attention based approach. Yeah, so this is what's going on. So this also talks about video and speech as possible modalities. Llama 3.2 uses cross-attention based approach. So no, he says something interesting here, like namely that in multimodal LLM development, we usually freeze the image encoder and only update the LLM parameters during training. Here, the researchers almost take the opposite approach. They update the image encoder, but do not update the language model's parameters. They write that this is intentional and done to preserve the text-only capability so that 11B and 90B models can be used as drop-in replacements for the Llama 3.1 and 7B model on test tasks. Yeah. So they use like, instead of using clip as the image encoder, they use some like VIT-H14 variant. Yeah, so that's pretty much it. Thank you. I hope you found this helpful.